A huge thanks to Brian for sponsoring this video. Video. I've won this ball at a fair. Never mind. We are back at integrals. This one right here is from the 2021 freshman maths competition from the University of Illinois. And we haven't done an integral in a while. And it's a fun one. I hope you're going to enjoy the video. By the way, in last time I'm working my wood really hard. So you should definitely check it out. Link to my second channel in the description. Check it out. The videos are cool. And now we are going to dive right in. So how would you approach an integral like this? There are many different ways, and the first thing that came to my mind is to factor the 1 plus x to the third power. If we were to factor it, we could use partial fraction decomposition or something of that sort. For example, you can also try some kind of substitution or like, I really don't know. So let us try to factor 1 plus x cubed, and then let's see where this is going to get us in the process. 1 plus x cubed is kind of a part of the geometric series, you can say. So if we have 1 plus x squared, we all know that we can turn this into the geometric series or geometric progression if it's just finite, being 1 minus x to the n plus 1 power, where n is the highest power, so x cubed, divided by 1 minus x. We all know how the geometric progression works. Now the thing is, we have 1 minus x to the third power. This is not good. We need 1 plus x to the third power. Now what about if we introduce the substitution x going to negative x? Then what we are going to get is, if we plug negative x into each and every x, we are going to get 1 minus x plus x squared, because negative x squared is the same as x squared, is equal to 1 minus, and then we have negative x but cubed. But this is negative times negative, positive times negative is negative. So negative and negative is going to cancel out, giving us 1 plus x to the third power. This is nice, divided by 1 plus x. And hey, here we go. We factored our 1 plus x to the third power into 1 plus x times 1 minus x plus x squared. Okay, what my hopes were when I initially did that was that 1 or x minus 1 and this factor right here, the smaller one, is going to cancel each other out. But this sadly doesn't work out. But let's still try the factorization in, and let's try out some partial fraction decomposition. So I is now equal to the integral from 0 to infinity of x minus 1 divided by, and then we are going to get a factorization 1 plus x times, and then x squared minus x plus 1. All integrate with respect to x. And now here my first hunch, since I couldn't do anything else, was partial fraction decomposition, meaning turning the multiplication in the denominator into some kind of addition of basically fractions, where each and every new fraction is going to have those ones as single denominators. Meaning what we're going to do is we're going to use the partial fraction decomposition ansatz, being that we want to turn x minus 1 divided by, so we have this polynomial of degree 1, x plus 1, and times this polynomial of degree 2, minus x plus 1. And all of this should be turned into some a divided by x plus 1. Why are we just choosing a up here? A is a real numbered constant or complex number, could also be, but we are having a real integral and we don't have any kind of singularities here, so we don't care about that. We are just using a because in normal case you could use any kind of nth degree polynomial really, but all of this would just be 0, all the coefficients. So just use a squared polynomial here, second degree polynomial, and you're going to see that all the coefficients of the higher degrees, x squared and x and whatsoever, are going to cancel out in the process, being just 0. Because we're going to compare coefficients later if you're not familiar with partial fraction decomposition yet. And then we are going to add, and now we are going to decrease the degree of the numerator by 1 of the degree of the denominator, meaning we're going to say this is plus some bx plus c divided by x squared minus x plus 1. And now what we can do under the condition that the denominator is not equal to 0, meaning we are just going to compare a bunch of things, we are going to multiply both sides by the big denominator, giving us that x minus 1 must be equal to. If we multiply a divided by x plus 1 by what we got right here, then x plus 1 and x plus 1 is going to cancel out, giving us just a times x squared minus x plus 1. So writing everything out is going to give us ax squared minus ax plus a. Same should be over here. The x squared minus x plus 1 is going to cancel out with this one, meaning we got bx plus c multiplied with x plus 1. Multiplying all of this out is going to give us plus bx squared plus cx. And then we are going to get just a single thing right here, plus bx plus c. And now all we have to do is compare coefficients, because two polynomials are exactly equal if their degrees are equal and also if their coefficients are equal. Meaning what we're going to do, let's group up the x squared terms at first. So we got this one right here and this one. So we got x squared times a plus b. Thus far, that's good. What we also got is everything with the x, so plus x times. So we got negative a, we got cx and also b. So we got b plus c minus a. And also the last part, so like the 0th degree part, is going to be just a plus c. So plus a plus c. Meaning we got a system of equations now, because what we want to do is we want to compare coefficients as mentioned before. On the left hand side we got a first degree polynomial, meaning the coefficients of the second degree on the right hand side must be equal to 0, giving us the first equation that a plus b must be equal to 0, or in other words a must be equal to negative b. Other than that, we are going to get b plus c minus a must be equal to, what's the coefficient of the x, is just 1. So we must have b plus c minus a must be equal to 1. Now we can plug our first condition in, namely that a is equal to negative b. If we were to plug this in, or b is equal to negative a, okay, this is the same formulation. We are going to get negative a but 2 times, so negative 2a. Plus c being equal to just 1, meaning if we were to add negative or 2a on both sides, we are going to get that c is indeed equal to 1 plus 2a. And our last condition is that a plus c must be equal to negative 1 if we were to compare the coefficients of the 0th degree polynomial part, meaning a plus c must be equal to negative 1. Meaning overall, if we plug our condition for c in, then we know that a plus, okay, then we are going to get 1 plus 2a. A plus 2a, that's an apple plus 2. More apples, analytic apple theory. We are still doing this, giving us 3 anal apples. Anal apples, oh goodness. That's the worst thing I have said in quite a while, is hence equal to negative 1. Or on the contrary, if we were to subtract 1 on both sides, we are going to get that 3a must be equal to negative 2, or in other words, a must be equal to negative 2/3. We can divide both sides by 3 because the successor of 2, so by definition not equal to 0. So we know what b is. B is negative a, so we also know that b must be equal to the additive inverse of negative 2/3, so just 2/3. And we also know that c is equal to 1 plus 2a. 2a is the same as negative 4/3. Meaning c is equal to 1 minus 4/3, so 3/3 minus 4/3 is negative 1/3, so c is equal to negative 1/3. That's a bunch of work, okay? Partial fractions is always so much fun, totally so much fun. Oh, I just love it. All mathematicians really love partial fractions. So if we were to plug this in, we get basically 3 integrals now. Since we can make use of the linearity of the integral to break it up. So we can break up this fraction into 2 other fractions, bring the coefficients to the outside, or I should rather say the constants, not with respect to x, meaning we are going to get negative 2/3 times the integral from 0 to infinity. And our numerator, this right here was our a, we brought it to the front of the integral. Our numerator, our denominator is x plus 1. So we get dx divided by x plus 1. And also what we get is, okay, so we are going to get bx, where b is 2/3, plus c. C is negative 1/3. We get a common factor of 1/3. Let us factor this out, bring it to the front. So 1/3 is a common factor, and then times the integral from 0 to infinity of. Now, we still have 2 left, so 2 times x plus, no, we don't have a plus, we have negative indeed. Negative 1 divided by, and our denominator is x squared plus minus x plus 1. All of this integrate with respect to x. And this is where we are at right now. That's an equivalent formulation for our original integral. Now what I did at the very first time trying this is, as usual, just with the square root of tangent, integral and the like, I broke up this integral into two more integrals. Like this one right here is really easy to integrate. You're just going to introduce the substitution, let t be equal to x plus 1, then you know that dt is equal to dx, then you get the integral of dt divided by t, which is obviously just the natural logarithm of t, where t is equal to x plus 1, meaning what we are going to get here, as the first part is going to be negative 2/3, the natural log of x plus 1, all evaluated from 0 to infinity. Now we get a small problem here. At 0, it's very nice, okay? Log of 0 plus 1 is log of 1, which is going to give us 0. It's just going to cancel out. But at infinity, log of infinity plus 1 is just infinity. Log of infinity, strictly increasing, is going to explode. And if you deal with the other two integrals, you're going to get a tiny little bit stuck, or I should rather say it's a huge mess, and I didn't want to go through that mess, so I just stopped there and tried a different method, and maybe you can write out what the different method could be. Here's just a little hint for the start. What I did, and to solve the integral extremely quickly, was break up this integral into two. So the integral from 0 to 1 of the integrand plus the integral from 1 to infinity of the integrand. Introduce a simple substitution and you are done in one line. But I wasn't really satisfied. I went back to this approach and I was fiddling a little bit around, and then I noticed something. Something really peculiar, and I was fucking stupid not doing this in the first place. Why did I break up this? Why did I break it up? Really didn't make any sense whatsoever, because if I take a look at the numerator, 2x minus 1, and compare it to the denominator, x squared minus x plus 1, that's just the derivative. Let us introduce a little tiny sexy substitution. Let t be equal to x squared minus x plus 1. So meaning if we implicitly differentiate both sides, we get dt is equal to 2x minus 1 dx. That is just our good old numerator. Oh goodness, I was being so stupid. This integral reduces so nicely. It's a competitive math problem. What did I think? Obviously it reduces nicely. Am I right, kitty catties? You haven't seen the kitty catties in a while. They are so hot. Look at all those hearts and the little teddy. Oh, that's so fucking kawaii desune. So let's write this bitch out. Meaning our integral I is hence equal to negative 2/3 log of x plus 1. And then we are going to get plus 1/3 the integral from, and now what we are going to get once we introduce substitution, let x go to 0, then this is vanishing, t is equal to 1. And obviously if you plug infinity into here, it's not too obvious, it's a limit problem, but you can factor out some stuff, break the limit up. You're going to see that the x squared is going to basically dominate the negative x. All of this is going to go to infinity. It's just a matter of few lines writing it out. Okay, you can compare polynomials basically by their powers, and x squared is always going to grow faster to infinity than basically x. Okay, and then we are going to get, so the numerator times dx is just our differential dt divided by, and we introduce that the denominator is just t. Okay, that is easy. That's once again just the natural log of t. Or in other words, if we bring it back to our original form, this is just the natural log of x squared minus x plus 1. It's that easy, and all of that from 0 to infinity, since we brought it back to our original variables. Now, that is cool. What we now got is, so we got this thing right here. We still need to evaluate it at infinity. I forgot about that, I'm sorry. And this part right here, if we evaluate it at 0, this is easy. 0, 0, log of 1 is just going to give us 0 once again. Then we are going to end up with the same limit. This part right here must go to infinity. So overall we have the limit as x approaches infinity on both. So I is equal to the limit. That's actually a nicely written limit for once. The limit as x approaches infinity of negative 2/3 log of x plus 1. And then we are going to get plus 1/3. And then we are going to get the log of x squared minus x plus 1. Now, is there anything else we can do? I mean, 1/3 is once again a common factor, just as before. We can bring it to the front of our limit. I'm going to denote the limit as capital L now to make it easier. So 1/3, the limit of. Now we are going to get negative 2 times the natural log of x plus 1 plus the log of x squared minus x plus 1. Now, if we have negative 2 times the log of something, this is the log of the something to the negative 2th power. So 1 over the something squared. The something squared, x plus 1, is x squared plus 2x plus 1, but just in the denominator. Meaning this part right here is just the natural log of 1 divided by x squared plus 2x plus 1. And now we got the addition of 2 logarithms, and multiplying, adding logarithms together is going to result in the multiplication of the arguments. Meaning overall we are going to get 1/3 times the limit as x approaches infinity of the natural log of x squared minus x plus 1 divided by x squared plus 2x plus 1. And simple asymptotics as you learned in school. Logarithm is a continuous function, meaning we can bring the limit to the inside. So the limit of the logarithm is just the logarithm of the limit, at least in the reals, and as long as the limit exists. And other than that, how can you basically get the limit of this thing right here? You just need to factor out the x squared basically on both the numerator and denominator. Meaning this is going to result in 1/3 times the logarithm of the limit as x approaches infinity. If we factor out the x squared on both numerator and denominator, they are going to cancel out obviously, or we can just expand both by 1 over x squared, really doesn't matter, giving us 1 as the leading number, plus, in our case minus at the top, plus. Then x divided by x squared is 1 over x. And 1 divided by x squared is just 1 divided by x squared, obviously. Other than that, we are going to get 2x divided by x squared, which is just 2 divided by x, and plus 1 over x squared. And if we now apply the limit rules, okay, applying the limit to both the top and the bottom and then applying it to all the summands, obviously 1 over infinity is going to be 0. 1 over infinity squared is still pretty fucking big, at least in the denominator, giving us 0 once again. This right here is 0 by the same arguments. This is 0 by the same arguments, meaning the limit is going to result in 1 in here, meaning our answer is 1/3 divided by the log of 1. And our answer is just really boring, because log of 1 is 0 and the whole thing is going to evaluate to 0, and that's it. So you see, partial fractions actually get you somewhere. They actually get you very nicely to your goal, even though they are really annoying to pull off all this factoring and then the algebra and the like. But I hope you still did enjoy this video, and if you did, if you want to see more problems like this, then why not make sure to check out the content of today's sponsor Brilliant, who are kind enough to sponsor yet another video here on this channel. If you're not yet familiar with Brilliant, let me give you a short and spicy introduction. Brilliant is an online learning platform and app with nearly 70 interactive courses in all topics STEM, be it the mathematics that we did today, physics, computer sciences, chemistry. No matter what it is you want to learn the STEM field, Brilliant definitely got something up the sleeve for you. And Brilliant, at least in my opinion, is by far the best source on the World Wide Web that you can use to learn something new every day. Their courses are just outright ridiculously good, and their animations are really something else and help you understand the problem at hand way better. It's just really hard to explain, and the best way to learn with Brilliant is by just trying it out for yourself, experiencing it on your own. But just as a little teaser, let me show this one to you. It's one of my most favorite examples. I'm also using it at school with my 6th grade. They are not speaking any kind of English, not very well, but they still understand what the graphics mean, and this really speaks for the quality of Brilliant by itself. Imagine you have a triangle. You want to find out what the sum of the interior angles is always going to be. Then Brilliant suddenly comes with this animation right here. You're going to track on the corners, blue, yellow, red, etc. You can see that if you switch the angles, just drag them around, play around with them, they are still going to add up to 180 degrees at all time. You're going to see the colors changing, okay, just changing ratios, but they are still going to keep their sum constant. And this is nicely demonstrated by just this little animation. And where this came from, they have way more. It's amazing. The whole website is flooded with those animations, graphics that you can play around with. And if this feels like something for you, if you wanna spark your curiosity today, learn something new, then why not make sure to check out the link at the top of the description, brilliant.org/flammablemevs. With it, you're going to get free access to a big portion of Brilliant already, but more importantly, the first 200 people to actually make use of the link get 20% off an annual premium subscription, which is a freaking great deal, considering how much content they already have available on their website and how much content they are adding on a regular basis. So definitely make sure to check it out and support the channel this way. And other than that, I don't have much more to say. And up until the next video, I wish you guys a day. Ciao.